my lab, we study quantum materials, an emerging class of materials that are changing how we understand electronics and how electrons behave. In traditional materials like copper or silicon, electrons mostly behave independently. But in quantum materials, electrons interact very strongly rather than acting alone. This gives rise to new and sometimes unexpected behaviors: superconductivity, magnetism, strange metallic states, or unusual insulating phases, all emerging from the same material. By exploring these systems, we're uncovering new physics and laying the foundation for technologies that conventional materials like silicon simply can't achieve. Quantum materials are special because their electrons interact so strongly that simple rules no longer apply. In everyday materials, if you understand one electron, you understand the whole system. But here electrons move together, creating collective effects that are rich and complex. At the Institute for Functional Intelligent Materials, we work with systems like twisted bilayer graphene, where two sheets of graphene, carefully rotated, reveal extraordinary new properties, as well as copper oxide superconductors and other low-dimensional compounds. These allow us to explore effects that could lead to faster, more energy-efficient technologies. We use terahertz radiation, a type of light that sits between microwaves and infrared, to probe how electrons behave inside quantum materials. Terahertz waves are very promising because they could power the next generation of ultra-fast wireless communication and imaging technologies. But terahertz radiation has been difficult to use. It's too fast for regular electronics and too slow for optical devices. In our lab, we found that when terahertz waves interact with certain quantum materials, they can trigger very fast electron flow. To harness this, we developed a new type of sensor called a viscous electron bolometer, a device that can detect tiny terahertz signals with extreme sensitivity and speed, responding within trillionths of a second. Potential applications are exciting. Ultra-fast terahertz sensors could drive the next generation of wireless communications, going beyond today's 5G networks. They could enable safer, more accurate navigation for self-driving cars, working even in rain, fog, or dust, where current sensors fail. They could also help transfer large amounts of data efficiently for virtual and augmented reality devices, smart city networks, and the Internet of Things. By developing new tools based on quantum materials, we are not only expanding what we know about physics, we're helping create the building blocks for the technologies of the future.